Here we're given three functions, and we need to show that these functions are linearly dependent on the real line. So in order to do that, we are going to show that there can be a constant multiple of these functions in such a way that the total sum equals 0. So we need to find the constants that we can multiply by f of x, g of x, and h of x, and have the total sum equal to 0. Now as we go about this, looking at our functions, the only ones that involve a x squared are a g of x and h of x. So let's try to figure out what we might need to do to make these cancel, and then see if we can get the constants to work out along with it. So we know that it's already a negative 3x. So in order for it to cancel with this 15x, let's see what happens if we multiply g of x by 5. That would give us a 10 minus 15x squared. Now let's see what happens if we just leave h of x alone. That would give us our 10 plus 15x squared. As we were hoping for, the x squared terms disappear, but the two terms add together to give us a 20. And looking now at f of x, it is only a constant term. So we could multiply the f of x, which is just the constant 5, by negative 4, and that would give us our 20, negative 20. So that it combines here, and that gives us our 0. Use the Wronskian to prove that the given functions are linearly independent on the indicated interval. So we need to show that e to the x, x squared, or x to the negative 2, and x to the negative 2 times ln of x are linearly independent on this interval. So we're only dealing with x values greater than 0. Let's quickly review what the Wronskian is. The Wronskian of indifferent functions is the n by n determinant, where the first column is first row, first column is the first function, and then as you go down the column, you just keep taking higher and higher derivatives of the function. So we have the first function, the first function, the first derivative, the first function and its second derivative, all the way down to the first function and the n minus 1 derivative. The next column just restarts the process at our second function, and then the second function's first derivative, and so on as you go down the column. So in our case, we have three different functions. So we'll be looking at the determinant of the 3 by 3. So let's list out this Wronskian, and then we'll talk about how to find the determinant. Our first function is e to the x, so we list e to the x here. We take the derivative of e to the x, and that's what goes in the same column but the next row. Derivative of e to the x is just e to the x. Derivative of e to the x again. And I know I'm going to end after 3 rows because I have 3 functions, so I should be expecting a 3 by 3. Now in our second column, we start with the second function, x to the negative 2, x to the negative 2, its derivative, negative 2, x to the negative 3, and then the second derivative, 6x to the negative 4. Now as we begin to take our final column, we have our x to the negative 2 times ln of x. This derivative is not going to be as quick as the others, so just off to the side, I'm going to write that out. The first derivative, we'll have to use product rule. Let's take this as our first term, bring down the power, subtract 1, leave the other term the same, plus first term left alone times the derivative of the other. And I think we can simplify this. This product becomes a x to the negative 3. So let's factor out a x to the negative 3, and we get negative 2 ln of x plus 1. So x to the negative 3 times negative 2 ln of x plus 1. And then let's find the second derivative using product rule again. This is our first term, bring down the power, subtract 1, leave the others the same, And then as we multiply by this derivative, we get negative 2 over x. And this becomes negative 2 x to the negative 4, so we can factor out the x to the negative 4. Negative 3 times negative 2 becomes positive 6. Negative 3 times the positive 1 there, minus 3. And then here we have the minus 3 minus 2, so that just combines to be a minus 5 when we combined those terms. So we've set up our Wronskian here. Now let's discuss how to take the determinant. These vertical bars are indicating that we have to take the determinant, and what we're looking for as a result is if the result of the determinant is identically equal to 0, then you know the functions are linearly dependent. However, after we take the determinant, if they're not identically equal to 0 on the indicated interval, then the functions are linearly independent. Now for a 2 by 2, the determinant is a lot nicer to work with. In a 2 by 2 case, you would just take the main diagonal, multiply those functions, and subtract it by the product of the off diagonal, and the determinant's very quick for a 2 by 2. In a 3 by 3, the calculation takes a bit more time, and one really nice way to organize it is to immediately rewrite the first two columns to the right. So we have our e to the x, e to the x, e to the x, our x to the negative 2, x to the negative 3, 6x to the negative 4. Okay, so adding these two columns just helps us keep track of things as we go through the process that I'm about to illustrate. First up, you start in the upper left corner, and you go down the diagonal, and we're going to multiply all of those together. And let me quickly kind of outline the process, and then we'll do it step by step. So you take this product, and then you add it by moving over, same first row but second column, and multiplying everything on this diagonal. And then add that to multiplying everything on this diagonal. And you know that you're done with that part of the process once you reach the bottom right corner. So up to this point, we've been multiplying and adding, multiplying and adding. Once you reach this bottom right corner, you start subtracting products. So then you come over to the bottom left, multiply everything on this diagonal, and that's what you subtract from the earlier groupings. Move over, multiply, and subtract. Multiply and subtract. And you know that you're at the end when you reach the upper right corner. Now, as y'all can see, for this determinant, we're dealing with rather complicated functions. Nothing's already 0, so a lot of these products are going to become somewhat complicated, and we're going to hope that things cancel out well as long as we keep up with the details and don't make any minor errors. So let's first write out these products where you add them and subtract them, and then we'll try to simplify terms, group, and simplify. So we have our first product, e to the x times negative 2x to the negative 3 times x to the negative 4, all times 6 ln of x minus 5. Okay. Plus, multiplying our next product, x to the negative 2 times x to the negative 3 times negative 2 ln of x, and that was plus 1. I need to watch those parentheses, times e to the x, times our last product on the going down this pattern, plus x to the negative 2 ln of x times e to the x times 6x to the negative 4. And now we begin the process where we go up the diagonals, subtracting. Now we subtract this next product, starting at the bottom left and going up the diagonal. E to the x times negative 2x to the negative 3 times x to the negative 2 times ln of x, minus our next product up the diagonal, 6x to the negative 4 times x to the negative 3 times negative 2 ln of x, plus 1 close parentheses times e to the x, minus our final diagonal, x to the negative 4 times 6 ln of x minus 5 times e to the x times x to the negative 2. So with these color coding and highlighting, hopefully we can see where these products came from. Let's distribute, and then we will see if we can group and cancel any terms, and we'll see whether this Wronskian is identically equal to 0 or not. So this first term, we know all of this gets multiplied by the 6 ln of x and the negative 5. So whenever we multiply it to the 6 ln of x, the 6 and the negative 2 combine to give us a negative 12. Let's write our x values first. The x's, same base, multiplied together, you add the exponents, that's x to the negative 7, times e to the x times ln of x. Okay. Now this times our negative 5 becomes a positive 10 times x to the negative 7 times e to the x. Okay, so we have simplified this first one, just put a check mark. And now these terms distribute here, and then here, and the e to the x is part of that. We have x to the negative 5 times negative 2 is our negative 2x to the negative 5 times e to the x times ln of x, plus x to the negative 5 times e to the x. Okay. So that one's done. Now this one, all that's left to do is just combine our exponents for the x terms. That is going to be 6x to the negative 6 times e to the x times ln of x. Okay, next up here we need to remember that we have this negative, and these terms all multiply together, and we get negative times negative 2 is positive 2, so we have a positive 2x to the negative 5 times e to the x times ln of x. So as we distribute these throughout, 6 times negative 2 is negative 12, but we're subtracting it, so that's a positive 12. X to the negative 7 times e to the x times ln of x. Distributed all now to the 1, and we get minus 6 x to the negative 7 times e to the x. That one's done. And our final one, we're distributing this throughout our 6 ln of x minus 5. We first get our negative x to the negative 6 times e to the x, and that is a negative 6. I should rewrite that. Times ln of x. Now we're subtracting the negative 5. That becomes a positive 5 x to the negative 6 times e to the x. And here we really want to be careful because any tiniest error could throw all of this off, and it would be really hard to catch after the fact. So let's see if anything will cancel. The first thing that jumps out to me is our first term here appears in its opposite form here, so these two will cancel out perfectly. Positive 12, negative 12 of the same thing cancels. Let's see if anything else cancels. Okay, I think up next we have this term cancels with this term. Okay, see if we have any more cancellation. Here, this 6 x to the negative 6 e to the x ln of x cancels with the negative 6 x to the negative 6 e to the x ln of x. And while the remaining terms don't cancel, I do think we can at least group these ones and then see if we can simplify algebraically the remaining expression. So let's turn the page and work on simplifying what remains of our determinant. Now 10x to the negative 7 e to the x minus 6x to the negative 7 e to the x leaves us with positive 4 of that. Okay. And now here, what we're going to do is we are going to factor out the common e to the x. And so that we can see things a bit easier, let's also factor out an x to the negative 7 from every term. That just leaves us with 4 for the first term. Now the e to the x factors out nicely from the second term, but we want to factor out x to the negative 7, and we have x to the negative 5th here. So whenever you factor out x to the negative 7 from x to the negative 5th, you're actually left with an x squared term, plus 5, the e to the x factors out. Factoring out x to the negative 7 from x to the negative 6 leaves us with a single x term. And we can rewrite this quadratic. And then we see it's nicely factorable, so we'll do that as well. So our Wronskian, after we've found the determinant of our 3 by 3 matrix, is this. And we need to remember that our initial condition for this problem was for x greater than 0. So let's ask ourselves, is this result always equal to 0? Or is it not equal to 0 for the given condition? Well, we know that e to the x is never 0. So it's not going to contribute to 0. Here, for x greater than 0, this is not equal to 0. And the only things that would make this equal to 0 is negative 4 here, negative 1 here. But so long as we're greater than 0, this doesn't equal 0 either. So the result is our Wronskian is not identically equal to 0. And if the Wronskian is not identically equal to 0, then our conclusion is that the functions are linearly independent. And the reason we went from this stage and we worked to factor it all down is we know very well when products of things are equal to 0, but left in this format, we couldn't have made the conclusion as surely as working it through to this factored form. So in this problem, we have a third-order differential equation that needs to satisfy these initial conditions, and we've been given 3 linearly independent solutions to this differential equation. And we're looking for a particular solution that satisfies these given initial conditions. So in this case, we can use the superposition principle and form a new solution. And we'll be able to determine what these coefficients should be based on these initial conditions. So for our first condition, inputting 0, we should end up with 0. E to the 0 is 1. E times 2 to the 0, also 1. So that really quickly becomes 0 equals C1 plus C2 plus C3. Now to use our next initial condition, we have to have the derivative. So let's take the derivative. Y prime is C1 e to the x plus 2 C2 e to the 2x, bringing down the derivative of the inside here through our chain rule, plus 3 C3 e to the 3x. Now this initial condition, when we plug in 0, we should get 0, and that will give us 0 equals C1 plus 2C2 plus 3C3. Now our final initial condition needs the second derivative. And whenever we input 0 here, we get the result of 3. So we have 3 equals C1 plus 4C2 plus 9C3. And this gives us with a system of 3 equations and 3 variables. And in order to solve this, we need to bring it into 2 equations and 2 variables. And we're going to do that through the elimination method. So first off, I think it might be really easy to eliminate the C1s because they're all the same term, unlike the C2s, which change coefficients, and the C3s. So let's take this times -1, and then we'll add that to the second one. So that gives us our -C1 minus C2 minus C3 all added to the second equation, which will result in 0 equals C2 plus 2C3. And then we can similarly multiply this equation by -1 and then add that to the third one and get our second equation in 2 variables. So this is -C1 minus 2C2 minus 3C3 added together will give us 0 equals 2C2 plus 6C3. And there is one quick error here. Adding the 0 and the 3 should have given me 3, not 0. Now if I multiply this equation by -2 and add it, we'll be able to get to an equation in 1 variable. So we end up with 3. That becomes our -C2 minus 4C3. So our C2's cancel perfectly, and we're left with 2C3, and that tells us that C3 must be 3/2. Now we can put that back into one of our earlier 2 equations, and we have that 0 equals C2 plus 2 times 3/2, which is just plus 3. That tells us that C2 is equal to -3. And now let's go back to our first equation to find what C1 is equal to. 0 equals C1 minus 3 plus 3/2. 0 equals C1 minus 3/2. When you combine -3 and a positive 3/2, you get -3/2. That tells us C1 also equals 3/2. So our particular solution that satisfies the given initial conditions is y equals 3/2 e to the x minus 3e to the 2x plus 3/2 e to the 3x. Now in this example, we have our given differential equation, we have our initial conditions, and we've been told our complementary solution and a particular solution. So we can find a new solution to the differential equation by taking our complementary solution and adding the particular. In that case, we would have C1 e to the 2x plus C2 e to the -2x minus 3. Let's follow through our initial conditions and we'll be able to determine what C1 and C2 should be. So for our first initial condition, we have 0 equals C1 plus C2 minus 3. We could rewrite that as 3 equals C1 plus C2. To use our next initial condition, we'll need to take the derivative. So our derivative is 2C1 e to the 2x minus 2C2 e to the negative 2x. Plugging in the initial condition, 10 is equal to 2C1 minus 2C2. Okay, and let's multiply the first equation by positive 2. That gives us 6 equals 2C1 plus 2C2. And then we'll add these together, and we get 16 equals 4C1, and nicely our C2's cancel. C1 must be 4. Okay, substitute that back into our first equation. 3 equals C1 plus, or C1 is 4. 3 equals 4 plus C2, so C2 must be equal to negative 1. So our solution that satisfies our differential condition, our differential equation, initial conditions, and our complementary and particular solution is y equals 4 e to the 2x minus e to the negative 2x minus 3.